So it's been 2 years since the last posting of our video lecture about the topics in line on the field of radiologic technology. So for today's video, we will gonna tackle about the concepts of radiation therapy. So we will begin, by looking at the history of radiation therapy, on how it was started and on how it was going as of today. Then it will then be followed by looking at the physics side, to radioactivity, to the different types of machine, down towards the most complicated part of radiotherapy. So this video, I think will be the most comprehensive video among the other lectures that I have done before. So I hope that you will be here up until the end of this video lecture. So let's begin by asking you this simple question. No. So what do you think about, or what do you know about radiation therapy? I'd like everyone to think of words or think about something that is related to radiotherapy. So by the end of this chapter, I will ask you the same question and see for yourself if you have learned new things or if you are already familiar. No, if you're already familiar with the basic concepts of radiation therapy. So to help us understand radiotherapy, we will start by defining radiation and therapy first. So radiation is defined as the emission or transmission of energy in the form of waves or particles through space or through a material medium. So therapy, on the other hand, is defined as the treatment intended to relieve or heal a disorder. So combining both definitions, we come up with a simple definition for radiation therapy. So radiation therapy is defined as the treatment of disease by the precise application of ionizing radiation. So we take note of the word ionizing radiation here. You have to remember that in radiotherapy, we are only constrained in using ionizing radiation. Okay, in radiation therapy, we have two basic forms. These forms actually only differ in the method of the delivery of radiation. So in the forms of radiotherapy, we are considering the relationship of the patient to the radioactive source. So first, we have the external beam radiotherapy and the internal beam radiotherapy. So your external beam radiotherapy, which is also called as here, the teletherapy, coming from the word tele, which means from a distance or from outside the patient's body. So yung internal beam radiotherapy can also be called as the brachytherapy, coming from the word brachy, which means short distance. So in external beam radiotherapy, the radioactive source or the dose is delivered from outside the patient using X-rays, gamma rays, or high-energy particles such as electron and protons. In external beam radiotherapy, we have to take note of the word outside. We have to take note of the word outside the patient because we use machines such as the LINAC to generate these radioactive sources and deliver the radiation to the patient from a distance or from afar. In internal beam radiotherapy, the dose is delivered from radioactive sources implanted in the patient, which makes the radioactive source closer to the target itself. So what do we mean when we say implanted? No, so the radioactive source can either be placed into a cavity or whichever the location of the tumor. So in teletherapy, we will discuss the different units used in external beam radiotherapy, such as the Kilovoltage teletherapy units, Megavoltage teletherapy units, and among others. While for internal beam radiotherapy, we have different techniques such as the intracavitary, interstitial, and others, which will be discussed in the succeeding chapters. Now let's move on the historical development of radiotherapy. So for the history of radiotherapy, We will have to look back from the beginning where Röntgen or Wilhelm Conrad Röntgen discovered X-rays in November 1895. Okay, so we are using X-rays in treating diseases. So it is important for us to remember this date. And again, I hope that this date is already in your mind because this is our foundation. Okay, on November 8, 1895, the discovery of X-rays. So the following year, months after Wilhelm Conrad Röntgen discovered X-ray, Dr. Emil H. Grubb, okay, specifically in January 29, 1896, he used ionizing radiation for cancer treatment. Okay, so after the discovery of X-rays by Röntgen, many physicians, many scientists, doctors actually use this discovery of X-rays into their clinical works, including Dr. Emil Grubb. Next, we have Dr. Leopold Freund in 1896. He used X-rays in the radiation of hearing moles of a 5-year-old child, and he also published the first textbook in radiation therapy. So this is the textbook that he published, entitled Elements of General Radiotherapy for Practitioners. So in the same year, in 1896, Robert J. van de Graaff developed his first model of the direct current electrostatic generator. So this is the image of an electrostatic generator. And in the succeeding chapters, again, we will understand the importance of this generator in radiotherapy treatment. In 1901, Dr. Alexander Danlos, he used the radium salts in brachytherapy for skin treatment of cutaneous lupus erythematosus. Next, in 1902, Dr. Clarence E. Skinner, he was the first to document a case of curing cancer using ionizing radiation. So this development actually led to many more studies on radiation as a specialty in medicine. No, okay, because what do you call this? During these times, the effectiveness of radiation as a treatment for such diseases is quite unsuccessful, and people are still skeptical about the effects of radiation. But this documented case of curing cancer opened the opportunity for a lot of doctors to use radiation in the treatment of many diseases. So in 1951, the installation of first cobalt-60 teletherapy units were done. In 1952, the first linear accelerator were installed. In 1960, the Paris system for brachytherapy were developed. So this cobalt-60, the linear accelerator, and the Paris system for brachytherapy will be discussed more further in the following chapters. But for now, or right now, we are focusing on the historical development of radiation therapy. And these images are the pictures of the development of radiotherapy throughout the years. Looking at the pictures, we see that the machines are quite large. No? They are quite large compared to our modern radiotherapy units, such as this. So, yeah, this is the modern linear accelerator. So, I'm showing you these pictures so that you have a clear picture of these machines as early as now. But we will discover and discuss more of these machines and units in the following chapters. So again, this is another image of the modern linear accelerator. Okay, moving on, we have the goals of radiation therapy. So when we say radiation therapy, it does not only mean to cure, cancer or to kill cancer or kill the tumor. We have other goals as well. So we have curative treatment and palliative treatment. So curative treatment is when we use radiation to kill cancer cells and cause minimal damage to normal cells in tissues surrounding the tumor. While in palliative treatment, we typically use this to relieve pain or to improve the quality of life of cancer patients, especially those in terminal stages. So in curative treatment, we aim in curing the patient and we aim to make them cancer-free by destroying the tumor itself. While for palliative treatment, we only try to improve their quality of life and to minimize the pain that they are experiencing. So that is all for the chapter 1 of radiation therapy entitled Overview and Historical Development of Radiotherapy. Okay, so we're done on the historical part and the introduction of radiation therapy. So we will gonna proceed on the physics of radiation therapy. Okay, so let's talk about the atom. So the atom is the smallest unit of matter and it possesses the physical and chemical properties of the elements. So the atom is composed of a positive core here, which is called the nucleus, and three fundamental particles. Okay, we have the proton, the neutron, and the electron. So the proton and the neutron is located inside the nucleus. So they are located in this part. They are collectively called as nucleons, while the electron is located in the orbital shell here. So they are located on the orbital shells, which they typically carry a negative charge. So the proton is considered to be the most important subparticle because it is equal to the atomic number of the element. The proton is equal to the atomic number of the element. Okay. It carries a mass in kilogram of 1.673 times 10 raised to negative 27, which is discovered by Eugene Goldstein in 1886. So the proton is considered to be the most important because an element cannot exist without a proton. An element cannot exist, it cannot exist without a proton, but an element can exist without neutron and electron. So that is why your proton is considered to be the most important among the three. So next is the electron, which is considered to be the lightest subparticle of atom because it carries a mass in kilogram of 9.910 times 10 raised to negative 31. So these electrons, they revolve around the nucleus and it was discovered by John Joseph Thomson in 1897. So what's special about electron is that it can behave as electromagnetic radiation. Your electron can behave as electromagnetic radiation primarily because it has mass. Meron nga siyang bigat. Take note that it has mass, it has electrical property, and therefore it has also magnetic properties. Okay, next is the neutron. So the neutron is the most unstable subparticle among the three because since it is unstable, which makes it responsible for radioactivity. So the neutron is the most unstable and it is responsible for radioactivity, as I have said before. So this neutron was discovered by James Chadwick in 1932 and it carries no charge. Okay, it has a mass slightly heavier than the proton, which is 1.675 times 10 raised to negative 27. So, makikita naman natin dito yung characteristic nitong tatlo. Makikita natin dito sa table. Nakasummarize na dito. So, an element is indicated by an alphabetical abbreviation called the chemical symbol. So, ito po yun, chemical symbol. The chemical properties of an element are determined by the number and arrangement of the electrons. So, in a neutral atom, the number of the electron is equal to the number of proton. Okay, so in this planetary model, here, the planetary model, we use the element helium. Okay, so let us see how the elements are represented to the chemical symbol. So as you can see, that the X here is the alphabetical abbreviation of the element, while the A is equal to the atomic mass number, which is equal to the number of nucleons, while the Z here, the Z represents the atomic number, or it also represents the number of the proton in the element. So in a helium atom, it has a total of 4 atomic mass number and 2 atomic number. So as you can see, or as you have seen in this planetary model, the atomic mass number is the total number of nucleons. So the helium atom has atomic number of 4 because it has 2 protons and 2 neutrons. 1, 2. We have 2 proton and 2 nucleons. Hence, it has atomic mass number of 4. Okay, so on the basis of different proportions of the neutron and protons in the nuclei, atoms have been classified in the following categories or nuclear families. So first we have the isotopes. So for our example here, we use the element barium because it has 7 naturally occurring isotopes, but I only included 5 in our example. So the isotope have the same proton or same atomic number, but different in atomic mass number and the number of neutron. So for our example here, barium has an atomic number of 56. Okay, so it has 56. So for these isotopes, we can see that they have different atomic mass number. So makikita natin dito magkakaiba sila na kanilang atomic mass number. So in order for us to get the number of neutrons, we only have to subtract the atomic mass number from the atomic number. So there we can see that these isotopes have the same atomic number or the number of protons, but differ in the number of atomic mass number and neutrons. Okay, so that is the isotope. So next is the isobar. So isobars, on the other hand, are atoms that have different number of proton and number of neutrons. Okay, so the similarity of these elements is the atomic mass number. So for our example, the element X has an atomic mass number of 30 and an atomic number of 15. So while the element Y has an atomic mass number of 30 and atomic number 14. So isobaric transition or isobars usually is present during the emission of positron in a beta decay. So in our example, element X here, the element X is the parent nuclei. Okay, while the element Y is the daughter nuclei. So the isobaric transition happens when the parent nuclei releases beta particle or a positron. Okay, so during this emission, the number of proton is decreased by 1. So mapapansin natin dito, from 15, naging 14 siya, nabawasan siya ng isa. Okay, so that makes this element isobaric. Okay, so from this parent nuclei, the daughter nuclei became a different element because the proton or the atomic number has changed. Okay, next is the isotone. So isotone has the same number of neutrons but different number of protons. Okay, and yeah, that also has the different atomic mass number. So for our example here, the element A has an atomic mass number of 40 and atomic number of 17, while element B, so the element B has atomic mass number of 43 and the atomic number of 20. Okay, so if we will gonna calculate the atomic or the neutron, the number of neutron, we will get the same answer, which is 23. And we can see that these elements have different atomic number and different atomic mass number, which makes them isotones. So the last category or the last family is the isomer, which the isomers have the same number of neutrons, the same atomic mass number, and the same atomic number. Okay, so for this classification, we will gonna use the technetium 99M. So I did not include the illustration of technetium 99M here. So because in isomeric transitions during gamma decay, typically hindi po nagkakaroon ng changes in their atomic mass number, in their atomic number. There is no change, or there is no release of particles. So the proton remains the same as well as the neutron. There is no change at all. What happens here is that the element only releases the excess energy, or the energy that is used. Okay, so that is the isomeric transition. So from technetium 99M, magiging technetium 99 na lang siya. So yung letter M, which stands for metastable or the excess energy, kapag nag-undergo ito ng transition, i-release niya ang kanya excess energy. So magta-transform siya into technetium 99. Okay. Ayan, ito pala, mayroon pala tayo dito. I forgot that I have included this. So, makikita natin dito, no, from technetium 99M. Okay, M stands for metastable or the excess energy. Once it undergoes a transition, it releases the excess energy, which is in the form of this letter Y. So, from metastable technetium 99M, magiging technetium 99 na lang siya. Okay, so let's talk about electron arrangement. So you have to remember that the maximum number of electrons existing in each shell increases with the distance of the shell from the nucleus. Okay, so it is determined by the equation n, or 2n raised to 2, where n is equal to the shell number. So the shell number is represented by the shell symbols K, L, M, N, and so forth. Okay, so remember also that the electrons, the number of electrons in the outermost shell, is equal to the group of the element in the periodic table. So for our example here, this element has 1, 2, 3, 4, 5, 6, 7, 8. It has 8 electrons on its outermost shell. So that means that this element belongs to the group 8 in the periodic table. And also, remember that the electrons in the outermost shell determines the valence of the atom. Nakadepende dito yung valence ng atom. So, the valence of an atom is further classified into two. We have the positive and the negative valence. We can say positive valence when there is less than 4 electrons on the outermost shell. Kung meron itong 4 or less na electrons sa pinakalabas dito, pinakalabas or the outermost shell of the atom. Okay. Remember that it is a positive valence when the number of electrons in the outermost shell is less than 4, no? Atoms with this valence belongs to the metals and conductors. Positive valence, they belong to the metals and conductors. While the negative valence, okay, so for the negative valence, the outermost shell has more than 4 electrons. So this example, okay, our example here, it has 8 electrons on its outermost shell. So we can say that this atom, okay, so this atom has a negative valence. And this negative valence atom, they are classified as non-metals or insulators. Okay, they are the exact opposite of the positive valence. And also, we also have atoms that has exactly 4 electrons on the outermost shell, which means that these elements are the semiconductors. Okay, remember also that the number of outermost electrons is equal to the period. Okay, so the element period in the periodic table. For the electron arrangement, you have to remember the octet rule. The octet rule states that no outermost shell should contain more than 8 electrons. So for our example here, This element has 8 electrons on the outermost shell. So you always have to remember that the outermost shell in any element must contain only 8 electrons. So that is the maximum number that the outermost shell of an atom can contain. And you might also be wondering, no, what makes these electrons continue to revolve around the nucleus? So that force is what we call the centripetal force, or the center seeking force. So the central seeking force is different from the electron binding energy, whereas the electron binding energy is the strength of attachment of an electron to the nucleus. So each electron on each shell has different electron binding energy. So you have to remember that the closer an electron is to the nucleus, that means that the electron is more tightly bound. So as the location of the electron, or as the electron is in the further shell, the lower is its binding energy. And you also have to remember that when an element or an atom is larger or more complex, the higher its binding energy, because the electron of atoms with many protons are more tightly bound to the nucleus than those of small atoms. So for large or bigger atoms or more complex atoms, it takes more energy for them to be ionized. Okay, so that's it for chapter 2. So we have previously discussed in chapter 2 the topics about atom and its fundamental particles, as well as nuclear structures and electron arrangement and binding energy. So now let's discuss the concepts of radioactivity. So in the previous chapter, as we all know, the nucleus is composed of the nucleons, which is the proton and the neutron. And I also mentioned that the neutron is the most unstable particle among the three. Now, take note that the stability of nucleus depends on the arrangement of the nucleons, particularly the number of neutron and the number of proton. And I have said that the neutron is responsible for radioactivity, thus an adequate number of neutron contributes to the stability of an atom. Please also take note that among many possible combination of neutron and proton, only 260 are stable and the rest are unstable. So there are actually three reasons or conditions when an atom is considered unstable or radioactive. So first, the atom can have too many neutrons. There are too many neutrons in the nucleus, or it can have too many protons as well. It can have too many protons in the nucleus, and it can also have both too many proton and too many neutron. So these three conditions or states makes an atom or a substance radioactive. So the unstable nucleus, either one of those mentioned, will sooner or later, from seconds to years, change to a more stable proton-neutron combination by the process of emitting or spitting out three particles, or in three forms. So it can emit mass in the form of alpha particle. It can also emit charge in the form of beta particle, and it can also emit energy in the form of gamma ray. So this phenomenon, or spontaneous emission of such particles from the nucleus, is what we call radioactivity. Okay? Now, while the atom or the substances that possess radioactivity, we call them radionuclides. So the atom or the substances that possess radioactivity is commonly referred as radionuclide. So when an atom is radioactive, there is a change from an unstable nuclide to a more stable nuclide. There is a need to change from the unstable state to a more stable state. So the unstable nuclide which undergoes radioactivity is what we call the parent nuclide. Okay, so this parent nuclide needs to undergo radioactivity since it is unstable, while the more stable nuclide, which the parent nuclide results to, is what we call the daughter nuclide. So this process of changing from an unstable condition or state to a more stable state is what we call radioactive decay or radioactive disintegration. So during this process of decay or disintegration, note that there is an emission of particles, nuclear particles, and release of energy as mentioned earlier. Now, radioactivity or radioactive decay is spontaneous. Ibig sabihin, tuloy-tuloy po ito, no? So, if spontaneous, this means that an atom can disintegrate or decay anytime without anyone knowing. And it can also be predicted. And aside from that, it is also impossible to know which radioactive atom will disintegrate first. So, yeah, this process is really spontaneous. Okay, so radioactivity can be found everywhere and it happens anytime without us noticing, and the radioactive substances can either be found in the nature around us or it can be created artificially. So it can be man-made. So in natural radioactivity, the radioactivity exists in nature. So it can either be cosmic or terrestrial radiation. So, cosmic natural radiation, when the cosmogenic nuclides is nanggagaling doon sa stars, sa sun, or on the moon. While for the terrestrial radiation or terrestrial natural radioactivity, they are found in the soil. It can be in the food we eat, as well in the water and in the air. Now, for artificial or man-made radioactivity, before artificial radioactivity, please take note that the background radiation for natural radioactivity is higher in altitude. Ibig sabihin, as the altitude increases, the intensity of radioactivity also increases. Okay, now, going back to artificial radioactivity or man-made radioactivity, this includes radiation fallout in nuclear power plants, nuclear ground testings. It also includes the cobalt-60 machines, which is used in teletherapy or the external beam radiotherapy. Also in smoke detectors, and of course in the radiopharmaceuticals, which are widely used in nuclear medicine. Okay, so these are the sources of radioactivity: natural and artificial. So the radionuclide which decays to attain stability is called the parent nuclide, as I have mentioned in the previous chapter. And the daughter nuclide is the stable form obtained. But take note that in some situation, the daughter nuclide can also be unstable. Okay, now, this unstable daughter nuclide will tend to lose energy by different decay mechanisms. So these are the following modes of radioactive decay. So we have the negative beta decay, positive beta decay, the electron capture, the alpha decay, and the gamma decay. So negative beta decay, which can also be called or referred to as beta minus decay, negatron decay, and negatron emission, in order for the nuclide to undergo negative beta decay, it must possess a neutron-rich and proton-poor condition. And the negative beta decay releases the negatron particle. So, negatron yung tawag doon sa nai-emit na particle. That is why we can also call this mode of decay as negatron emission or negatron decay. So, this type of radioactive decay is used in nuclear reactors. So, for example, we have a nuclide with an atomic number of 12 and atomic mass number of 40. Now, I want you to write in a paper for this example. So, we have a nuclide of nuclide X, with an atomic number of 12 and atomic mass number of 40. So, notice that this nuclide is proton poor. Now, to calculate the number of neutron, we need to subtract the atomic mass number, which is 40, by the atomic number, which is 12. So the number of neutron in this nuclide is 28, thus meets the condition of having a proton-poor and neutron-rich nucleus. Now in beta minus decay, a neutron is converted into a proton, so during this conversion, a negative beta particle is released accompanied by antineutrino. This antineutrino is a massless and chargeless particle which is a byproduct of the nuclear conversion. So basically itong antineutrino is just there. So kasama lang niya itong si beta particle. So together with the negative beta particle, we call the negatron, which is the particle release in negative beta decay. So the parent nuclide X, as I have mentioned, decays to a daughter nuclide Y, having 13 atomic number and the same atomic mass number. But notice that the number of neutrons decrease as the number of protons increase by 1. So this transition of the parent nuclide X to the daughter nuclide Y is called isobaric transition. So, the parent nuclide and the daughter nuclide have the same atomic mass number with different proton and neutron number. So, this transition, the daughter nuclide will possess an excess energy as a result of the release of the particle. Now, at this moment, the daughter nuclide daughter nuclide is still unstable, so it needs to continuously undergo negative beta decay to become more stable. But remember that with excess energy, the daughter nuclide cannot proceed to another negative beta decay until it has excess energy. So it has to undergo a gamma decay to release this excess energy. So the daughter nuclide Y with atomic number 13 and neutron number of 27 and atomic mass number of 40 will release the excess energy through gamma decay. So the transition of the daughter nuclide Y to release the excess energy is called isomeric transition. So isomeric, as previously discussed, do not have any nuclear changes. It only releases the energy through the gamma decay. Now, after this transition, after the release of the excess energy, only then that the daughter nuclide can undergo another negative beta decay, and so on and so forth until it becomes stable. So this process will repeat until the nuclide becomes stable. Now, for positive beta decay, basically it's just the exact opposite of the beta minus decay, except that it produces different particle of different charge. So the positive beta decay can also be called beta plus decay, positron decay, and positron emission. So a nuclide must have a proton rich and neutron poor nucleus. No, so negative beta and the positive beta decay also differ in terms of its application. Okay, so for positive beta decay, it releases a particle called the positron and is used in cyclotron. Okay, so for positive beta decay, it releases a particle called the positron and is used in cyclotron. So we will discuss more of the positron and the cyclotron in the following chapters. For the decay process, for example, an element X has atomic number 35 and a mass atomic number of 50. So we have to calculate again the number of neutrons, which is equal to 15. So you see that this element is proton rich and neutron poor, making it possible to undergo this type of decay. So in contrast to the negative decay, the positive beta decay converts one proton into a neutron. It converts one proton to one neutron, which means that the daughter nuclide Y will have an atomic number of 34 and a neutron number of 16, while it has the same atomic mass number. So during this conversion, it releases a positive beta particle accompanied by a neutrino. Okay, so a positive beta particle and a neutrino, magkasama yung dalawa na nare-release. So together, ang tawag dito is positron. So the positron is equivalent to a mass of electron, only with a different charge, which is positive. So the release of positron is coined as annihilation. Okay, the release of the positron is called annihilation, the process by which the element or the nuclide emits positron. Okay, and again, the transition of the parent nuclide to the daughter nuclide is an example of isobaric transition. Okay, so it's safe to say that the daughter nuclide at this point is already stable. Okay, so is it safe to say that the daughter nuclide at this point is already stable? Okay, so the answer is no. No? So just like the negative beta decay, the daughter nuclide needs to keep decaying in the same process until the ratio of the number of neutrons and protons or the nucleons as a whole becomes acceptably stable. Okay, and again, at this point, the daughter nuclide possesses excess energy, so it has to undergo a gamma decay first to release this energy. So after the gamma decay and after the release of the energy, it can now proceed to the next beta plus decay to reach a more stable state. So the process will repeat until the daughter nuclide reaches its passive stable state. So a nuclide with proton-rich and neutron-poor nucleus can decay in beta plus decay, as discussed in the previous slide. But it can also decay in electron capture by the process of electron capture. So for both decay and nuclide, the nuclide must have a low number of neutron, and it can be increased first by the process of converting the proton into a neutron by releasing a beta particle. And second, by the proton absorbing the inertial electron into the nucleus to form a neutron, so that is your electron capture. So the absorption of the K shell electron into the nucleus is the reason why this decay is called electron capture, because the proton or the nucleus absorbs the electron in the K shell to compensate the ratio of the number of protons to the number of neutrons. So for example, we have again the element X with atomic number of 34 and mass number of 50. So the nuclide has 16 neutrons before the decay process starts. So what happens here is that the parent nuclide will have to capture the electron into the nucleus. So during this absorption, the nuclides undergo isobaric transition as well. Now, how did the proton able to capture the electron, or how did the nucleus able to capture the electron? Now remember that the proton or the nucleus is positively charged, and we all know that the electron is negatively charged. So opposite charges attract. Okay? So the proton having the positive charge attracts the electron. And when a proton and a neutron collides, it becomes a neutron. Now, the daughter nuclide Y will have 17 number of neutrons and 33 number of protons after the first transition. So during this process, the nuclide loses an inertial electron. So more specifically, a K shell electron. So the space occupied by the inertial electron is now free because the electron is absorbed into the nucleus. It will be vacant. So what is going to happen next? The electron from the outer shell will have to occupy the vacancy of the K shell. So this process is what we call the electron cascade or electron transition. And another thing to remember that during the electron cascading, radiation is produced. Now, what type of radiation yun na po produce? Diba sinabi sa busyong that when an when an outer shell electron fills the vacancy of the inner shell electron, it emits radiation, and that radiation is called as the characteristic radiation, or more specifically, K-characteristic radiation kapag yung vacancy na na-fill is doon sa may K shell. Okay, it is the K-characteristic radiation because the electron is captured from the K shell and the vacancy filled is the K shell. And because the electron and there's more, okay. Now, where does the K characteristic radiation go? So the radiation now propagates away from the atom. Now, as the characteristic radiation is produced, there is a possibility that an outer electron will be ionized. Remember that the K characteristic radiation has energy high enough to ionize an electron. So if this characteristic radiation hits an electron, the electron will be ionized. So this ionized electron by the characteristic radiation is what we call the OZ electron. It is the OZ electron spelled as AUGER. Okay, it is pronounced as OZ electron. So this whole process from the parent nuclide to the daughter nuclide and all the particles and radiation produced will be repeated until the nuclide reaches a more stable state. For the alpha decay, or we can also it alpha emission. So the radionuclide involving this decay are those nuclide containing a very high atomic number and very high neutron number. So the condition of the nuclide must be proton-rich and neutron-rich. Usually, these radionuclides have an atomic number which is equal or greater than 82, while for the atomic mass number, it must be greater or equal to 180. So these radionuclides are what we call the heavy nuclides, okay? Because of their neutron to proton ratio in the nucleus. So during this decay, the particle or the parent nuclide emits 2 proton and 2 neutron, and that is equivalent to a helium atom. So for example, we have a parent nuclide with an atomic number of 95 and a neutron number of 100. So that means that it has an atomic mass number of 195. So when it undergoes alpha decay, the daughter nuclide will have an atomic number of 93 and a neutron number of 98 and an atomic mass number of 191. So during this transition, the daughter nuclide will have, if the daughter nuclide have an excess energy because of the transition, it has to undergo the same process of gamma decay to release this energy before it can proceed to another alpha decay until it reaches a more stable state. So we are now at the final type or mode of radioactive decay. So this is internal conversion. So we have been mentioning for many times that the excess energy can only be released through gamma decay. So it involves excess energy. It means that it has an excited nucleus after a transition. So that's just one way of releasing this energy or making the excited nucleus relax. So the same thing with internal conversion. It makes an excited nucleus stable by losing its energy. It's just that it is different in the process. So for the internal conversion, it emits the energy by interacting with the orbital electron. So the process of the internal conversion can actually be likened to photoelectric effect, where the gamma ray escapes in the nucleus and then it interacts with the orbital electron. So the process after the exposure to the gamma ray or gamma radiation, the electron can be ionized, thus ejected in the orbital shell. So in this process, it can also be likened to the electron capture. There will be an electron cascade or what we call this or electron capture, electron transition, because an electron is ejected during the internal conversion. As discussed in the case of electron capture, the ejection of the orbital electron by the internal conversion will create a vacancy on the involved shell, which is called your electron cascade. This results in the production of characteristic radiation. Again, when a characteristic radiation escapes the atom, it has a tendency to ionize another electron of the same atom, which produces your OZ electron. Understood? Okay, so that is your internal conversion. Okay, so we are now done with the basic physics of radiotherapy. So we will now move on to the teletherapy units. Under teletherapy units, we have two classifications. First is the kilovoltage teletherapy units and the megavoltage teletherapy units. So for this chapter, chapter 4, we will discuss the kilovoltage teletherapy units. Under the kilovoltage teletherapy units, we have 4 subclassifications or types. First is the Grens ray, the contact therapy, superficial therapy, and the deep therapy. So these machines or these units operate or generate X-rays with voltage up to 300 kilovoltage peak. Okay. So on the about 1950s, Most of the external beam radiotherapy was carried out with the use of kilovoltage teletherapy units, but subsequent development of higher energy machines, and the increasing popularity of the Cobalt 60 machines gradually resulted to the demise of the conventional kilovoltage machines. However, even with the popularity of the higher energy machines or the Cobalt 60 machine, the kilovoltage teletherapy units have not completely disappeared. Hindi pa rin sila totally nawawala in the present time. Okay, so there are still who use lower energy beams, especially when the treatment is for superficial skin lesions, where they still use kilovoltage teletherapy units. So first, let us discuss Grens ray. So the Grens ray are the X-rays that produce at potentials below 5 to 20 kilovoltage. Grens ray therapy is used to describe the treatment with beams of very soft X-rays. Very soft, sobrang baba kasi ng kilovoltage na ginamit. Low energy siya, okay? Low energy, which means that the penetration is also low. Okay, so low depth penetration. Hindi siya masyadong nakaka-penetrate. The Grens ray, although at this present time, are no longer in use, especially in radiotherapy. It is not being used anymore because it is not effective for treating tumors located deeper, okay, or slightly deeper, because it only can be used for dermatological application, okay, and the skin. That is where it is usually used before for dermatologic use and for treating nickel-sensitive patients, suppressing allergic contact dermatitis. So basically, it was used for skin allergies, dermatological problems, and other forms of skin problems. You know. So Grens ray therapy are used for that, but at this point, it is no longer being used. So next is the contact therapy. Okay, the contact therapy, or we can also call it endocavitary endocavitary machine. It operates at potentials of 40 to 50 kilovoltage, and it facilitates irradiation of accessible lesions at very short SSD. SSD, or the source to surface distance. The machine, it usually operates at a tube current of 2 milliampere, okay, 2 milliampere only. So applicators available with such machine, the contact therapy units can provide a source to skin distance or SSD of 2 cm or less. For the applicators, we will learn more about applicators in the following chapters. Okay, so for contact therapy, we are also using 0.5 to 1 millimeter thick aluminum filter, and it is usually interposed in the beam. It is interposed in the beam, and it absorbs the very soft or the very low energy rays in the beam that are not useful for the treatment process. So the clinical applications for contact therapy, they are used for tumors not deeper than 1.2 millimeter, and it's used to treat superficial skin lesions. The contact therapy, we also call it endocavitary machine because it is used it was mostly used for the treatment of superficial rectal cancers. Okay? Rectal cancers. That is why we call it endocavitary. Next is the superficial therapy. So the term superficial therapy applies to the treatment with X-rays produced at potentials ranging from 50 to 150 kilovoltage. So they use low energy Krebs tube, okay, for superficial therapy. So various or varying thicknesses of filtration, usually 1 to 6 millimeter aluminum, are added to harden the beam. Okay, beam hardening. So the degree of hardening or the beam quality can be expressed as the half value layer. So ano nga ba itong half value layer? So yung half value layer, it is defined as the thickness of a specified material, okay? Thickness of a material that when we introduce it into the X-ray beam, kapag in-introduce natin yung material na yon, it reduces the exposure rate by one half. Okay, it reduces the exposure rate or the energy of the beam by one half. So the SSD for superficial therapy is 15 to 20 centimeter, and the superficial treatments are usually the given with the help of applicators or cones. Okay, applicators or cones which are attached or which is attached to the diaphragm of the machine, okay, to help make the beam harder for beam hardening. So the superficial therapy is useful for tumors confined to about 5 millimeter deep. So beyond this depth, tandaan natin na kapag lumagpas na siya sa 5 millimeter depth, the dose is too severe to deliver adequate dose without considerable overdosing of the skin surface. So it is risky because when we deliver over than the calculated dose, when we go over the 5 millimeter depth, there can be overdosing of the skin. So dapat sakto lang. Sakto lang tayo or limit within the 5 millimeter depth. So that is for superficial therapy. Next is the deep therapy, or we can also call it orthovoltage therapy. So the term deep therapy or orthovoltage therapy is used to describe treatment with X-rays produced at potentials ranging from 150 to 500 kilovoltage. So medyo mataas na siya dito. So most of the orthovoltage equipment is operated at 200 to 300 kilovoltage. Okay? So the range 150 to 500 kilovoltage range lang yon. Okay, but most of the equipment or most of the machines usually yung range nila is 200 to 300 kilovoltage. It also uses or it operates with 10 to 20 milliamperes. So again, various filters can be used or are designed to achieve half value layer between 1 and 4 millimeter Curie. Okay? So again, same application, the filtration, it is used for absorption of the low energy X-rays in the beam that is not useful for the treatment. Cones can be used, okay? Cones to collimate the beam into a desired size. A movable diaphragm consisting of lead plates. It permits a continuous adjustable size. So, parang sa collimator din na X-ray machine natin, no? So, the SSD is usually set at 5 cm or 50 cm. Okay, 50 to 70 cm. Yun yung range natin ng SSD. So, the deep therapy or orthovoltage therapy is used for tumors within 2 cm depth. So, medyo malalim na yung kaya niyang i-treat. But we have to realize that the maximum dose occurs close to the skin surface. Okay? 90%. 90% of the delivered dose to the tumor is happening or is absorbed in the skin surface. So in a single field treatment, okay, and in the following chapters, we will also discuss treatment techniques that we have. For example, the single field treatment. Okay, so when we use single field treatment using an orthovoltage machine, adequate dose cannot be delivered to a tumor beyond this depth. So what we can do is to use several beams that is directed to the tumor from different directions. And we can also use a higher dose to compensate in such a way better treatment or higher dose is delivered into the tumor. So kapag single treatment lang or single field lang, single field treatment kasi, ang ibig sabihin nun ay isang beam lang yung ginagamit natin. Pero we can use several beams directed into the tumor to deliver the desired dose using deep therapy. Okay? Yun yung pwede natin gawin. So, the deep therapy or the orthovoltage therapy has several limitations or disadvantages. So, as I have mentioned earlier, the skin dose is very large. Okay? Because 90% of the dose or the beam is absorbed in the skin surface, making the poor or making the depth dose distribution poor. So the depth dose distribution is the amount that is being absorbed in the surface and into the deeper surface of deeper locations of the tumor. So hindi maganda. Hindi nagiging maganda yung distribution. It can be very high in the skin surface or very low into the location of the tumor. Next is the increased absorbed dose in the bone. Ito naman, it means that when the tumor is located behind a bone, okay, kung yung tumor natin is located inside the cavity or a bone, the dose is mostly absorbed by the bone. Na-absorb siya ng bone, making the dose that is delivered to the tumor very low or inadequate. So yung desired dose na gusto natin i-deliver sa tumor ay hindi natin na-achieve because it is absorbed by the bone. So in order to achieve a desired dose, we can also use several beams, okay, or multiple beams. There are other techniques, okay, that can also be used, such as this sparing the skin, which we will be discussing more of those techniques in the following chapters. And last disadvantage is this increase in scattering, okay, increase in scattered radiation. These disadvantages make the orthovoltage beams unsuitable for the treatment of tumors, especially with those tumors behind bones or to those deep-seated tumors.